Hello friends, welcome to our YouTube channel. We have learned that an electrical network is called a two-port network when it comprises of one input port and one output port. We can describe a two-port network in 6 ways. Each method uses a set of 4 parameters. As all the sets of parameters describe the same two-port network, there exist definite relationships between them. Today we shall establish interrelationships between Z parameters and the other sets of parameters. Let us first recall how Z parameters are used to describe a two-port network. In this method, port currents I1 and I2 are taken as independent variables and port voltages V1 and V2 are considered as dependent variables. Therefore, linear equations used to express V1, V2 in terms of I1, I2 are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. These two equations can be written in matrix form as follows. Matrix of V1, V2 equals to matrix of Z11, Z12, Z21, Z22 into matrix of I1, I2. Or this can be simply written as matrix of V equals to matrix of Z into matrix of I. The elements of Z matrix are known as Z parameters. These parameters can be determined by open circuit tests, therefore they are known as open circuit impedance parameters. They are measured in ohm. Let us first derive interrelationships between Z parameters and Y parameters. When we describe a two-port network using Y parameters, we express the port currents I1 and I2 in terms of port voltages V1 and V2. The linear equations used in this case are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. These two equations may be written in matrix form as follows. Matrix of I1, I2 equals to matrix of Y11, Y12, Y21, Y22 into matrix of V1, V2. Or we can write matrix of V1, V2 equals to inverse matrix of Y11, Y12, Y21, Y22 into matrix of I1, I2. When we describe a two-port network using Z parameters, the linear equations used may be written in matrix form as follows. Matrix of V1, V2 equals to matrix of Z11, Z12, Z21, Z22 into matrix of I1, I2. Comparing these two sets of equations, we get matrix of Z11, Z12, Z21, Z22 equals to inverse matrix of Y11, Y12, Y21, Y22. Or we can write matrix of Z11, Z12, Z21, Z22 equals to 1 upon delta Y into matrix of Y22 minus Y12 minus Y21 Y11, where delta Y equals to Y11 Y22 minus Y12 Y21. Therefore, we get Z11 equals to Y22 by delta Y, Z12 equals to minus Y12 by delta Y, Z21 equals to minus Y21 by delta Y, and Z22 equals to Y11 by delta Y. Now we have obtained Z parameters in terms of Y parameters. Let us derive expressions for Z parameters in terms of transmission parameters. When we describe a two-port network using transmission parameters, we express the input port variables V1, I1 in terms of output port variables V2 and I2. The linear equations used in this case are V1 equals to AV2 minus BI2 and I1 equals to CV2 minus DI2. By rearranging the second equation, we get V2 equals to 1 upon C times I1 plus D upon C times I2. By using this expression in equation number 1, we get V1 equals to A into 1 upon C I1 plus D by C I2 minus B I2. Or we can write V1 equals to A by C I1 plus AD minus BC divided by C times I2. When we describe a two-port network using Z parameters, the linear equations used are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing the expressions of V1, we get Z11 equals to A by C, Z12 equals to delta T by C, where delta T equals to AD minus BC. Now comparing the expressions of V2, we get Z21 equals to 1 upon C, Z22 equals to D by C. Now we have obtained Z parameters in terms of transmission parameters. Now let us derive expressions for Z parameters in terms of inverse transmission parameters, or simply called T dash parameters. When we describe a two-port network using inverse transmission parameters, we express the output port variables V2 and I2 in terms of input port variables V1 and I1. The linear equations used in this case are V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. Now, by rearranging the equation number 2, we get V1 equals to D dash by C dash times I1 plus 1 upon C dash times I2. By using this expression in equation number 1, we get V2 equals to A dash times D dash by C dash times I1 plus 1 upon C dash times I2 minus B dash times I1. By rearranging this equation, we can write V2 equals to A dash D dash minus B dash C dash divided by C dash times I1 plus A dash by C dash times I2. Now, when we describe a two-port network using Z parameters, the linear equations used are V1 equals to Z11 times I1 plus Z12 times I2 and V2 equals to Z21 times I1 plus Z22 times I2. Now, comparing the expressions for V1, we get Z11 equals to D dash by C dash and Z12 equals to 1 upon C dash. Now, comparing the expressions for V2, we get Z21 equals to delta T dash by C dash, where delta T dash equals to A dash D dash minus B dash C dash, and Z22 equals to A dash by C dash. Now, we have obtained the expressions for Z parameters in terms of T dash parameters. Now let us derive expressions for Z parameters in terms of hybrid parameters. When we describe a two-port network using hybrid parameters, we express the input port voltage V1 and output port current I2 in terms of input port current I1 and output port voltage V2. The linear equations used in this case are V1 equals to H11I1 plus H12V2 and I2 equals to H21I1 plus H22V2. By rearranging the equation number 2, we can write V2 equals to minus H21 divided by H22 times I1 plus 1 upon H22 times I2. By using this expression in equation number 1, we can write V1 equals to H11 I1 plus H12 into minus H21 by H22 times I1 plus 1 upon H22 times I2, or we can write V1 equals to H11 H22 minus H12 H21 divided by H22 times I1 plus H12 divided by H22 times I2. When we describe a two-port network using Z parameters, the linear equations used are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. By comparing the expressions of V1, we get Z11 equals to delta H by H22, where delta H equals to H11 H22 minus H12 H21 and Z12 equals to H12 by H22. Now comparing the expressions of V2, we get Z21 equals to minus H21 by H22 and Z22 equals to 1 upon H22. Now we have obtained the Z parameters in terms of hybrid parameters. Now let us derive expressions for Z parameters in terms of inverse hybrid parameters, or simply called G parameters. When we describe a two-port network using G parameters, we express the input port current I1 and output port voltage V2 in terms of input port voltage V1 and output port current I2. The linear equations used in this case are I1 equals to G11 times V1 plus G12 times I2, and V2 equals to G21 times V1 plus G22 times I2. Now rearranging the equation number 1, we get V1 equals to 1 upon G11 times I1 minus G12 by G11 times I2. Using this expression in equation number 2, we get V2 equals to G21 times 1 upon G11 times I1 minus G12 by G11 times I2 plus G22 times I2. Now rearranging this equation, we get V2 equals to G21 by G11 times I1 plus G11 G22 minus G21 G12 divided by G11 times I2. When we describe a two-port network using Z parameters, the linear equations used are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing the expressions for V1, we get Z11 equals to 1 upon G11 and Z12 equals to minus of G12 by G11. Comparing the expressions for V2, we get Z21 equals to G21 by G11 and Z22 equals to delta G by G11, where delta G equals to G11 G22 minus G21 G12. Now we have obtained the expressions for Z parameters in terms of inverse hybrid parameters. Let us now solve a couple of numerical problems to implement the interrelationships developed so far. We have to find Y parameters for the pi network shown. Also, we have to determine Z parameters using interrelationships. The impedance offered by the inductance ZL equals to J omega L, that is equal to 0.01 S ohm, where S equals to J omega under steady state condition. Let the port voltages be V1 and V2 and port currents be I1 and I2. Let us mark the nodes 1 and 2. Applying Kirchhoff's current law at node 1, we can write I1 equals to V1 by 5 plus V1 minus V2 divided by 0.01 S. Therefore, we can write I1 equals to 0.2 plus 100 by S times V1 minus 100 by S times V2. Now, applying Kirchhoff's current law at node 2, we get I2 equals to V2 by 10 plus V2 minus V1 divided by 0.01 S. Therefore, we can write I2 equals to minus 100 by S times V1 plus 0.1 plus 100 by S times V2. The linear equations used while describing a two-port network using Y parameters are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. Comparing these two sets of equations, we get Y11 equals to 0.2 plus 100 by S mho y12 equals to y21 equals to minus 100 by S more, and y22 equals to 0.1 plus 100 by S more. So we have obtained y11 equals to 0.2 plus 100 by S more, y12 equals to y21 equals to minus 100 by S more, and y22 equals to 0.1 plus 100 by S more. Therefore, delta y equals to y11 y22 minus y12 y21 equals to S plus 1500 divided by 50S more square. Now let us use the interrelationships to find Z parameters. Z11 equals to y22 by delta y, that is equal to 5S plus 5000 divided by S plus 1500 ohm. Z12 equals to minus y12 divided by delta y, that is equal to 5000 divided by S plus 1500 ohm. Z21 equals to minus y21 by delta y, that is equal to 5000 divided by S plus 1500 ohm. Z22 equals to y11 by delta y, that is equal to 10S plus 5000 divided by S plus 1500 ohm. The transmission parameters for a two-port network are given as A equals to 7 upon 2, B equals to 15 upon 2 ohm, C equals to 3 upon 2 mho, D equals to 7 upon 2. We have to determine Z parameters using interrelationships. We know for transmission parameters delta T equals to AD minus BC. Putting the values we get delta T equals to 1. We know Z11 equals to A upon C, that is equal to 7 upon 3 ohm. Z12 equals to delta T upon C, that is equal to 2/3 ohm. Z21 equals to 1 upon C, that is equal to 2/3 ohm. And Z22 equals to D upon C, that is equal to 7 by 3 ohm. Here H parameters for a two-port network are given as H11 equals to 1000 ohm, H12 equals to 0.003, H21 equals to 100, H22 equals to 50 into 10 to the power minus 6 mho. We have to determine Z parameters using interrelationships. We know delta H equals to H11 H22 minus H12 H21, that becomes minus 0.25. Now we are using the interrelationships. Z11 equals to delta H by H22, that is equal to minus 5000 ohm. Z12 equals to H12 divided by H22, that is equals to 60 ohms. Z21 equals to minus H21 by H22, that is equal to minus 2 into 10 to the power 6 ohms. Z22 equals to 1 upon H22, that is equal to 20 into 10 to the power 3 ohm. So today we have established interrelationships between Z parameters and the other sets of parameters. With the help of these interrelationships, we can easily find z parameter when we have another set of parameters readily available. Finally, we have solved a couple of numerical problems to have hands-on practice to implement these interrelationships. So that's all I have for you today. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.